All right, in this video, we are going to learn how to write and predict products for single and double replacement reactions. So a single replacement reaction is one in which an element is going to replace another element in a compound. So here is the general form. It can happen one of two ways. So either, as you can see, B and C switch places. And remember, in Unit 6, Unit 5, we learned that the thing written on the right is the anion, so the negatively charged ion. So either those can switch places, or, oh, wrong one, underline the wrong one, or the cation can change places. So as you can see in this one, A and C are the one that change places. This is not a good representation of it, but pretty much the way that you determine what's going to switch with what is the element unit by itself. You need to determine whether it's a metal or a non-metal. All right, so this is the question you need to ask yourself. Is it a metal or a non-metal? All right, if the element by itself is a metal, you're going to switch it with the thing that's in the front. If it's a non-metal, you're going to switch it with the thing that's in the back, or the second thing. All right, so here's another example. So A is by itself and B and C are dancing, but then A is going to take its place, take B's place. Now, in order to figure out if a cation is going to replace one another, we have to use what's called the activity series, because some metals are more reactive than others. So sometimes a reaction can happen, sometimes a reaction won't happen. So we use this activity series to determine which is going to happen. Here is a picture of the activity series. So the ones listed at the top are going to be more reactive, whereas the ones written at the bottom are going to be less reactive. So when you are determining whether a reaction is going to happen, you want the thing by itself to be listed higher than the thing in the original compound. It'll make more sense when we do in some practice. But again, the thing by itself needs to be higher on the list. All right, that's in terms of metals. For nonmetals or anions, typically we're only going to see the switching of halogens, which are group 17. And with halogens, you just have to see where they rank on the periodic table. Fluorine is the most reactive nonmetal, and it decreases as you go down. So you want the thing that is by itself to be higher up on the periodic table. So if you're comparing fluorine and chlorine, and fluorine was by itself, it could switch. If chlorine was by itself, the reaction would not happen. They would not switch places. All right, again, kind of sounds confusing, but we're going to do some practice. So here are some examples of single replacement reactions. So here I have zinc by itself. Is zinc a metal or a non-metal? Zinc is a metal. So that means in this reaction, the cations are going to be switching places. So that means zinc and hydrogen are going to switch places. And thankfully for this one, it kind of already shows us that it switched places. All right, so as you can see, the zinc took the place of the hydrogen, and then the hydrogen's by itself. Now, something I do want to point out, you still have to think about swap and drop, all right? So what they did is that they know zinc always has a +2 charge. Chlorine's in group 17, it has a -1 charge. Swapped and dropped to get the ZnCl2 formula. All right, and then remember, hydrogen is one of your diatomics, so you have to list it as such. So that's why you list it as H2. Now again, you always have to make sure your reactions are balanced. So reactants, products, ZnHCl, one zinc, one hydrogen, two hydrogens, one chlorine, two chlorines. So the way to balance this reaction would just to be put a 2 in front of that HCl. All right, now looking at the next one. So here we have calcium solid and reacting with lithium hydroxide. Again, the thing that's by itself, is calcium a metal or a nonmetal? It's a metal, so it's going to switch with the other metal or cation in this compound, which is lithium. All right, so when they switch, that means calcium and hydroxide are now going to be together. Calcium has a +2 charge. Hydroxide has a -1 charge. So when you swap and drop, it would be CaOH2. And then remember, your hydroxides are insoluble. So this is going to be solid. Plus lithium, which is a metal, so it's solid. Now, I went ahead and gave you the products for this reaction, but go ahead and look to see if this reaction can even happen. Since I know this is a metal and I know I'm switching cations, I need to go back and use the activity series. So I need to see if calcium is listed higher than lithium. All right, so here's lithium. All right, it's at the top of the list, and here's calcium. So that means this second reaction is not going to be able to happen. All right, so instead of writing all the products, I'm actually just going to write NR. NR equals no reaction. All right, so now let's look at the next one. All right, again, I have zinc by itself. We determined before that it was a metal, so this is a cation switch. So if you don't want to have to do all the hard work and then realize you have to erase it and put no reaction, go ahead and check your activity series first. All right, so if I look, here is zinc and here is lead. So since zinc, the thing by itself, is higher than lead on this activity series, then this reaction is going to happen. All right, which means that zinc and lead are going to be the ones to switch places. To write the formula for zinc sulfate, Zn 2 plus, SO4 2 minus, swap and drop. So it'll be Zn SO4, and sulfates are soluble. All right, plus lead by itself, which is a solid. Then you would need to balance this reaction, and in order to do that, just about all of these would get a 2. I kind of quickly did that. You could go through the chart if you wanted to, but I'm kind of going through that quickly because you've had now a lot of practice with it. All right, our last one, KBr and Cl2. So here is the thing by itself. Cl2 is a nonmetal, which this means the anions are going to switch, which means Br and Cl are going to switch. If you look on the periodic table, Cl is above bromine in group 17, so this reaction can happen. So to write KCl, be K plus, Cl minus, swap and drop to be KCl, and that is aqueous, plus Br2, and it is a liquid. All right, then finally, you would have to balance the equation, and you would do so by putting 2's in front of KBr and KCl. So that is single replacement reactions. Double replacement work very similarly to single replacement, except you don't have to guess whether or not the reaction will happen. Chances are it is going to if I've given it to you. And with these reactions, two things are going to switch places. So the main thing that you have to be able to identify here is the cations and the anions, because you have to make sure You're swapping the right two things, okay? So what I mean by that, let's look at this first one. H2SO4. I know that hydrogen, when it adopts when it becomes an ion, it adopts a H plus charge. And SO4 I know is sulfate, and the formula for sulfate is SO4 2 minus. All right, and then calcium is a metal, so it adopts a positive charge. It's in group 2, so it adopts Ca plus 2. And then chlorine is in group 17, and it's a non-metal, so it's going to adopt a -1 charge, which means that I always swap the anions. It doesn't matter which two you swap in terms of swapping the cations or the anions. I always swap what's second because it makes the most sense to me. So I'm going to swap the SO4 and the Cl minus. So when I do that, it's going to become H plus and Cl minus. So when I swap and drop, that's HCl, and that is aqueous, plus CaSO4, which is a solid. All right, now your last step would be to balance this, and the only thing you need to do to balance it is this one. All right, same thing here. It might help you to write what the anion is, or not anion, what the ion is above your formulas, just so that kind of helps you in your when you're writing the products. So potassium is a metal, and it adopts a positive charge, group 1. So it is K plus 1. PO4 I know is phosphate, so that's PO4 3 minus. All right. Iron, it is a metal, so I know it's a positive charge. Iron's a transition metal, so I don't always know what the charge is going to be. So I do know, however, that oxygen is a nonmetal, which forms an anion, and it is always going to have a -2 charge. So that means if I have 2 oxygens in this formula, if I were to unswap and drop, this would be Fe plus 2 and O minus 1, which I know is wrong, but if I multiply both of these by 2, I would get O minus 2 and Fe plus 4. So this had to be the charge of iron to get to that correct formula. So that's another thing just to be mindful of. That's a more advanced problem that you would see. I prefer to swap my anions, swap whatever you feel led to do. You still keep the charge. If it's a transition metal, you keep the charge the of the transition metal. You don't change it when doing the reactant side. All right. So this would now be K plus O2 minus, which would be K2O. And this is going to be aqueous, plus we have Fe plus 4, PO4 minus 3, swap and drop, Fe3, PO4, 4, solid. And then this one I'm going to work out because it gets a little funky. And I can't really do this off the top of my head. So reactants, products. Okay. I'm going to keep the PO4s together. It's easier to balance them that way. And then Fe and O. So if I have an O in a PO4, I'm not going to count that towards my total O's. So I have 3 Ks on the reactant side, 2 on the product side, 1 PO4 on the reactant side, 4 on the product side, 1 iron on the reactant side, 3 on the product side, and then 2 oxygens on the reactant side, and 1 oxygen on the product side. I'm going to balance out the PO4s first, so that I'm going to put a 4 out here, which then this turns 3 to 12. So in order to get 12 Ks on this side, I'm going to put a 6. So that now turns into 12. and then that turns my oxygens into 6 on that side. And then in order to get those to have 6, I need to put a 3. So this now has 6, and this now has 3. So this is balanced. And then, let me erase that. So then here are just some pictures again of how to do double replacement. Again, this example shows the cation switching. I again prefer to do where the anions are switching, personal preference. All right. And then the last thing I do want to touch about briefly is net ionic equations. So when we've been writing our chemical equations, we've been talking about having aqueous solutions. And then typically with an aqueous solution, they're made up of ionic compounds. However, because it can dissolve in water, that means that our ions are actually going to separate, okay? Like when you dissolve salt in water and it disappears, that because it's going to break down from NaCl to Na ions and Cl ions. All right, so this is saying, however, the equation above does not show this dissolution. And so we write what is called a complete ionic equation, and it shows us how those ionic compounds dissociate into ions. So complete ionic equations show us what are called spectator ions. So these are the things that are on both sides that are actively involved in the reaction, which just means that they're not producing what we're looking at in an equation, or they're just kind of there. All right. So as you can see, we have AgNO3. When I wrote, or in order to get this formula, I knew I had Ag plus 1 and NO3 minus 1. So in a complete ionic equation, it's showing you those individual ions in water. Now, again, NaCl is salt. All right, so Na and Cl, those broke apart. AgCl, so since this is a solid, this is not going to break apart in water. So this is what stays together. So in our complete ionic equation, it stays together. And then finally, NaNO3, aqueous, I know it was Na plus and NO3 minus. So it breaks apart when it's dissolved in water. So this is the complete net ionic equation. It shows us everything that's happening from our original equation. Then we have net ionic equations that only show us the elements or formulas that are participating in the reaction. This does not include spectator ions. All right, and to write a net ionic equation, all you need to do is make sure that if you have elements or compounds, if you have ions that show up on both sides of your equation, on both sides of the arrow, you need to kind of cancel those out. And I say that air quotes, all right? Cancel them out because they're not a part of the reaction we're trying to see, so we don't want to show them in our equation. So from the equation on the last slide, Ag plus NO3 minus plus Na plus Cl minus yields AgCl, Na plus, and NO3 minus. Again, since that NO3 appears on both sides, we do not include it in the net ionic. The same with Na. However, this silver ion and this chloride ion are reacting to create that silver chloride salt. All right, so that's why we do include it in our net ionic reaction. All right, I know that was a lot of information, but if you have any questions, please feel free to let me know.